Isabel, the Fair Image Data Steward of Euro-BioImaging. And in this session, we will be discussing simple steps and current developments towards making bioimaging data fair. As you remember from the FAIR Basics section, metadata is important for many of the FAIR domains. And I only here quickly want to mention what is metadata. So in general, metadata is data about the original data, and it provides the information needed to enable the discovery, interpretation, and reuse of the data. And of course, the type of metadata you have to record depends on the type of the original data. So for example, when we regard data as the product here, the olive oil, then metadata is the labels on the bottles, which can contain either basic or extensive information on the original data and be both human readable or in a machine readable format. And according to the NFDI for Bioimage Data Management survey that I already mentioned in the first talk, over 80% of respondents agree that metadata is essential, but only 30% find it easy and time-saving. On the right here, you see the top 3 improvements that the respondents identified to close this discrepancy. And the first one is that they wished for more guidelines for which metadata has to be recorded for which purpose. And yes, I totally agree that this is currently a major point in bioimaging, but also, unfortunately, this is quite a tricky point because of the previously mentioned heterogeneity of bioimaging experiments. But it is actively worked on in the community, and I only want to quickly show you some examples that are currently tackling this problem. One of those are the recommended metadata for biological images, or REMBI, which is quite a high-level metadata scheme that contains these 8 categories from information on the study, the specimen, the image acquisition or data analysis, and some finer-grained keywords that should always be reported with an imaging experiment. And this scheme is currently applied by the Bioimage Archive, so you will hear more about that in the coming talk. But there's also some more advanced and more complex metadata schemes, like, for example, the OME data model from the open microscopy environment that is implemented by the Image Data Resource, which will also give a presentation later. And in addition, there is the 4DN BINA OME tiered metadata model. And unfortunately, we don't really have time to go deeper into any of those, but you get the links to these tools and models so you can inform yourself further. But this is just for you to see that there is currently progress in the community to work on that problem of the missing guidelines for which metadata should accompany which imaging experiment, and which, unfortunately, as I said, is far from easy. But the development of metadata standards has to go hand in hand with the second improvement, the software for metadata collection, which of course need to know which metadata to collect. One tool here that is currently being developed in the community is the MicroMeta app that allows you to create a virtual representation of a microscope and all of its parts. So this then can be reused for every experiment that uses this microscope. This can be then combined with the image acquisition settings of an individual experiment, and a metadata file for that experiment can be exported. And this MicroMeta app is built upon the 4DN BINA OME metadata model we have seen earlier. Working together with the MicroMeta app is Methods J2, a plugin for Fiji that takes the image metadata which it gets from reading in an image through the bioformats library, and it combines it with the metadata from the MicroMeta app, and thereby creates a default methods text for journals, which aims to close the current reporting gap of microscopy metadata in journals. In addition, there's MDEMIC, metadata editor for microscopy, that allows you to easily edit the image metadata to improve the interoperability between different microscopy assays. And MDEMIC is part of the standard installation package of the image platform Omero. Now, Omero itself, which stands for OME Remote Objects, it's not just about metadata, but what it is a central and secure client-server-based platform that allows you to handle, view, and organize and share your images from everywhere. So because it's a client-server-based platform, this means that a facility sets up an institutional Omero server, and scientists can set up clients that connect to the Omero server from anywhere to visualize, manage, and annotate their image data. And as I said, Omero can do many things, which we unfortunately don't have time to go into. But on the metadata aspect, it stores the metadata, including the acquisition metadata and user-edit annotations, as well as also ROIs and segmentations in a relational database, thereby making also the pre-publication data more fair and reproducible. And the third improvement on metadata is to improve the user-friendliness of ontologies. But what are ontologies in the first place? Here's the two problems that ontologies are trying to solve. One is that we have different words for the same concept, as in different names for the same microscopy technique. But also, we have sometimes the same word referring to different concepts. And an ontology tries to solve these problems by displaying the properties of a subject within an area and how different subjects are related inside that area by defining a set of categories and relations that can represent subjects in that area. And you have probably used ontologies without realizing. But for example, if you have ever described your organism using the NCBI taxonomy. But of course, also for other areas, ontologies have been created, and you can find them using EMBL EBI's ontology lookup service. So for bioimaging here, I want to show you these two examples. The biological imaging methods ontology, FBBI, that is used by current imaging repositories like the IDR and Euro-BioImaging. So the next actionable step for scientists is to go to one of those ontologies and look up the appropriate ontology term of your imaging method, but maybe also your organism, your sample preparation method, and so on, so that we have them properly documented now and have them already present for data deposition. On the facility side, it is valuable to install one of the metadata tools that I mentioned, like for example, the Micrometa app, and create representations of the microscopes in your facility, or Omero. And with that, make one step towards better metadata recording. This enhanced metadata recording is also one of the crucial factors identified by some of the European projects that were already mentioned in the previous talk, such as, for example, the BioCovid project, through which I am funded. And the BioCovid project takes SARS-CoV-2 and other infectious diseases data that come from many sources and have therefore quite variable formats and standards. And it mobilizes, connects, and standardizes that data so it can be combined and exposed on the COVID-19 data portal, making it thereby easier to find, access, and analyze the data by scientists, policymakers, or anyone interested. And BioCovid works in tandem with another EU-funded project, the Isidore project, that provides free of charge access to scientific services for research on epidemic-prone diseases, which currently has open calls for you to get free access to scientific instruments for research on these topics. So you can scan the QR code or go to the website if you're interested. But why I'm mentioning this here is that Isidore and BioCovid are working together in a way that the data generated through Isidore gets directly fed into the pipelines that are developed in BioCovid. And on the other hand, BioCovid makes sure that the data coming out of Isidore is of good quality and recorded according to the FAIR standards. And one of the crucial outcomes of these two projects working together is that research data management is very important to enhance the fairness of data. Also, nearly 90% of people from the NFDI for Bioimage survey agreed that data management increases the quality of science, but nearly as many state that they need to learn more about it. And one great place to do so is the RDM kit, which provides short articles on different research data management aspects and topics within the life sciences. And many of these funders, like the Isidore project, but also more and more universities, are now demanding to have a data management plan to accompany each research project. And such a data management plan describes the journey of the data, all the way from creating the data through to publication and storage of the data. And it thereby details information on the general project description and roles and responsibilities in the project, and then goes into which data gets used and collected, how data and metadata are documented, how the data is stored and preserved, and later shared and accessed, as well as provides information on any ethical or legal issues. And it is most beneficial to think about all of these aspects even way before any data is collected. And thereby it's important to start with the data management plan before the beginning of the project, but also to update it regularly during the project, so that at the end of the project, you have a traceable record of what happened to your data. Now, the format of such a DMP can be as simple as a Word or PDF document, and we at Euro-BioImaging are currently developing a bioimaging-specific DMP template as an offer for our nodes with targeted questions for bioimaging projects. But also, going beyond simple text documents, a DMP can be more elaborate, using one of these tools, for example, the Data Stewardship Wizard, DMP Online, or Argos. But there's also others around. But here you can create smart questionnaires that are targeted to specific research fields or even projects, so that researchers only see the questions that are relevant to their projects. And in addition, these DMPs can be shared with multiple parties, and at the end, a DMP file in different formats complying with different funder requirements can be exported. So regardless of the format, on the facility side, it would be valuable to distribute a data management plan template alongside with data management guidelines, so that on the other hand, scientists can start early in writing a data management plan and also updating it during the project. So now we have many times talked about the actual part of sharing data and how central that is for fair data. But only 13% of the NFDI for Bioimage Community Survey respondents have already shared data, but 64% say they would do it in the future. So here on the right, we have the current 3 biggest hurdles for data sharing. And at least for the largest point, the lack of guidance on appropriate repositories, we will tackle this in the remainder of this workshop. So here I will only quickly talk about the different types of repositories and leave the details to the other speakers. So in the best case, we have domain-specific repositories that are specialized to one type of data or subject area. And those can be further subdivided into open repositories, like the ones we will be hearing later in this workshop, like the Bioimage Archive, Empire, and IDR in the domain of bioimaging. But there's also restricted access repositories for sensitive data, such as the Cancer Imaging Archive in the bioimaging domain. On the other hand, if no domain-specific repository exists, there are also general purpose repositories that take any kind of data, including manuscripts for publications, for example, like Zenodo, Triad, BioStudies, and Figshare. And then there's also some institutes that provide own repositories, like, for example, the Swedish SciLife Lab hosts one. So on the facility side, it is valuable to inform the users about the possibilities of data deposition, be it your own institutional repositories or domain-specific repositories, whereas the next point for scientists is to find a domain-accepted repository, which in the domain of bioimaging, you will most likely have accomplished by staying for the rest of this workshop. And when you go on to actually deposit your data in one of those repositories, to get a persistent identifier for your data set to make it findable. Speaking of persistent identifiers, they don't only exist for data, but they also exist for researchers and facilities. Most of you will have heard from the Open Researcher and Contributor ID ORCID, but something similar also exists for research organizations, the Research Organization Registry, or RORF in short. And this way, you can properly identify and acknowledge people and facilities that were part of the project. So the last action point for scientists is, if you have not done so already, get yourself an ORCID and then make sure to properly acknowledge persons, facilities, and fundings that were part of the data creation or data analysis. And on the facility side, request a ROR and provide it to the users to get properly acknowledged. Extra points here for Euro-BioImaging nodes. You can request yourself to be linked to the Euro-BioImaging hub, but this linking also applies for any facility that have some kind of relations to other facilities. So by following all of these points, your data will probably not be 100% fair. But by getting started with these points, some of them really only take a few minutes, this will get you on the fair pathway, and the resulting bioimage data will be considerably more fair. Especially if many people engage in this together, then together we can move the field of bioimaging towards a fairer state.